Hello everybody and welcome at the Petroleum Systems Analysis webinar. This is presentation number 4 and one session that will be given by Alan Burnham. I think most of you know Alan's name in association with the widely used Vitrinite reflectance model. It was developed
1989.
Alan developed this as a co-author when he worked at Lawrence Livermore National Laboratory, where he spent about 30 years of his life. And later on, he went on to American shale oil, and now he's a consultant and working as an adjunct professor at Stanford University. Now, Alan, it's yours now.
Well, good morning or evening, whichever it is, wherever you are in the world. This presentation is an extension of what I presented at the AAPG meeting in Calgary in June. Ken Peters and Oliver Schenk were contributors to that particular presentation. I've expanded, including some stuff that was done at the time but not included, and also some other things that I've done since to kind of complete some work that was partially done at the time. So the fact that you're here, you probably already know all this. It's an important parameter for calibrating paleothermal histories. This presentation is really not going to talk about how to do that. It's really going to talk about the underlying basis of the chemical reaction models to predict it. So it's not truly a basin modeling presentation. It's really a chemical kinetics presentation. And I have to state at the outset that all models of Vitrinite reflectance, or for that matter of organic maturation in general, are approximations, and you need to validate them at the time temperature conditions of application. It'd be nice if we knew these things precisely, but the fact is that we always have to calibrate them due to the approximations that are made. There have been many variations of these models developed over the course of history, and I'll go through some of that history. But the fundamental question is, which is the most reliable and why? And I wish I could give you a definitive answer, but I think there is still some uncertainty in this aspect, and we'll talk about that. So here's some information going back way back in history. And I'm sure you've all seen these kinds of diagrams showing that an immature kerogen has some aromatic material and some aliphatic material, a fair amount of oxygen, and these chemical features determine the hydrogen index as well as the reflectivity. And as the material matures, the aromatic material is selectively concentrated and to some extent created. The amount of oil and gas that are generated is proportional to the aliphatic material, but there is some net generation of aromatic material. Now, the reflectivity of any material is related to the polarizability of the constituent molecules, and aromatic materials tend to be quite polarizable, and you can relate both the refractive index and the absorption to the electronic spectrum, and the Fresnel-Beer equation is what you can use then to calculate those parameters. For the materials of interest, we're talking about dominating the reflectance being dominated by the size and orientation of the aromatic rings. Vitrinite reflectance becomes anisotropic at high maturity because of the selective orientation of the aromatic rings. Here's a brief review of the models that have been developed over the years. Doug Waples popularized the Lopatins TTI in this, I believe, in the late 70s, perhaps early 80s. It was based on the simple concept that chemical reactions double with a 10-degree increase in temperature, but of course that's not really chemical kinetics per se. That's more of a rule of thumb for cooking. We came along and said, well, okay, we can do better than that. We can actually base it on chemical reactions as we believe are occurring, and that is the Vitrimat model. In a similar time frame, Wood and Emico developed the Arrhenius TTI, which is using an activation energy more comparable to oil generation, but still had certain features related to the TTI. They called it a TTI. And then the IFP built a model based on the transformation ratio. That's in Burnham's book. And also then there was a competing thought by Barker at USGS saying that the Vitrinite reflectance was related to the maximum temperature. So here at the outset you see the range of possibilities, and at the one end, the Lopatin method said that the reflectance was very, very sensitive to time, and at the other extreme, Barker's model saying no, time wasn't really important, it was just temperature. It turns out that the chemical reaction models were in between, and that was one of their strengths that was recognized fairly quickly. So in this time frame, well, in the 60s and 70s, there was a method of kinetics called the isoconversional kinetics, and this was used by Suzuki and Waples to develop another model of reflectance called simple RO, and at the same time, we've simplified Vitrinite to create EZR0, which it is not as fundamentally based. It's really calibrated against Vitrimat. It's not calibrated really against any other data. It's actually meant to reproduce the Vitrimat model using the hydrogen to carbon correlations. At the same, when these things were developed, personal computers were fairly new, and computational speed was actually quite important. So we looked at various ways of speeding the computation by simplifying the chemical reaction network, and they're not really published in the peer-reviewed literature. They're available in Lawrence Livermore reports. These modifications of EZR0 and Vitrimat. Today, people are really not that concerned about computational time, so they've just kind of lost their importance. However, one of the interesting aspects of computational time is the power law approach, and that was used by Huang at Exxon, and then later by Bayon and all. So that's a very rapid way of calculating chemical reaction conversion. Other people have taken the parallel reaction model, Ritter, Carr, Zhangping, and Nielsen, and have modified the parameters. It's a structure which is very, very similar to EZR0, but it's substantially different from the power law approach. And we'll talk about that here in a moment. The underlying issue is that the Vitrinite is a complex organic material. There's not just one chemical reaction which is changing its reactivity. There's lots of chemical reactions, and they vary in their rate. And when you have a distribution of reactivity, you have to use a chemical reaction model which acknowledges that. On the left-hand side here, you see there's a variety of ways of doing that. One is the isoconversional method, which says that the activation energy and frequency factor depend on the extent of conversion. It's very common now, perhaps even dominant in thermal analysis. There's the power law in time, which is a very simple model, and mathematically it's very similar to a gamma distribution and frequency factor. There's the pseudo nth-order reaction, again, fairly simple, and it's also mathematically close to a gamma distribution in the frequency factor, and then by implication a power law in time. And you can also use continuous distributions. Gaussian and Weibull distributions are two examples which are commonly used. You can also use a gamma distribution of energy, and I think Henschel's book mentions that. And then finally there's the discrete distribution. Most people use a common A with a variation in E, but you can also have A vary with E, and a pretty standard way of doing that is saying that the logarithm of A is equal to A plus BE. On the right-hand side, you see an nth order Gaussian distribution that has been fitted to sintering data. And I want to emphasize the point that distributed reactivity is not just for chemical reactions. It can also be for physical processes like Oswald ripening. And in this particular case, we interpret the variation in frequency factors, the variation of diffusion lengths, and activation energies, a distribution of the kinds of defects that affect the rate of diffusion. So all this stuff has been known for decades. I want to point out that there really are a variety of approaches that are mathematically different from the discrete energy distribution that most people use in petroleum geochemistry. Here's now an added slide. This just gives the correlation for a curve that's in Burnham's book, and the blue, it's just a simple read the points off the plot and use Excel to fit the parameters. They probably have an equation which is available someplace. I don't have it. Maybe some of you do, but the point is here that it turns out that it fits very similar to EZR0. I mentioned previously that EZR0 is a simplified model of Vitrimat correlated to hydrogen to carbon correlation of Vitrimat. The equations governing Vitrimat are shown on the left-hand side. They're really just elemental balance equations written down for assuming that there are four products: water, carbon dioxide, higher hydrocarbons, and methane. And then these are the activation energy distributions for those four reactions. Each one is considered to be a complex reaction. There was some confusion at the beginning saying that these were determined by open pyrolysis. That's really not true. Open pyrolysis was taken into consideration, but confined pyrolysis was really the main source of data that was used to calibrate Vitrimat. Now, so EZR0 essentially says we have activation energies ranging from the mid-30s to the high 70s or mid-70s, and this said, okay, let's see if we can just have one global reaction taking care of all that. And of course, there's enough parameters that you can fit the curve so you can get a simpler approach to calculating the same thing. But I want to emphasize that EZR0 again is not calibrated to data directly. It's calibrated to Vitrimat, which was in fact calibrated to confined pyrolysis conditions and geologic conditions. Here's a couple of plots showing how you can use an nth order reaction. Again, what the parallel reaction model tries to do is spread the reactivity over a broader range of time temperature conditions. An nth order reaction, as I mentioned, is equivalent to having a gamma distribution of frequency factors. And we're talking not about a true nth order reaction, but a pseudo nth order reaction. And so you can see that it takes fewer reaction channels to get the same spread of uniform reactivity. And it's an approach which I was a little surprised nobody has picked up, but it's people are pretty well entrenched, I guess, with the first order reactions. There's something in the literature called Vitrinite reflective suppression. There's a paper by Price and Barker from 1985 in the Bakken Formation showing the suppression of Vitrinite, and this is a very commonly shown figure showing this. So the question is, why is the Vitrinite reflectance suppressed in this Bakken? One hypothesis is that it's overpressuring due to overpressuring that in the generating interval, and perhaps some of the audience here have explored that issue. And experimental studies indicate that pressure can be important, but probably not enough, and I'll show that data. A second hypothesis is because of the interaction of Vitrinite with bitumen. There's a paper which by Barker in 2007 where they took the samples extracted the bitumen from the sample and then remeasured the same material, and they found that it was not important. In other words, the swelling of the vitrinite at the time of measurement is not a significant factor. However, that does not mean that the vitrinite and the oil components may not have reacted prior, either in diagenesis or in the early stages of metagenesis. So you can't completely discount this, at least from the data that I've seen. The third possibility is it's merely just a different kind of vitrinite. If you consider coal, the deposition conditions are really quite different from type 3 organic matter that may be in a marine sediment, as it could have been altered in the water column. So these are all the issues that might be important, and as far as I know, people still are arguing about this with no clear consensus. So let's go back to Huang's work at Exxon. Very nice paper. If you haven't read it, I highly recommend it. They did closed tube pyrolysis. They found that the vitrinite reflectance depended on the HI of the coal. This is all at the same pressure, so this immediately suggests that the presence of the saprophilic matter does in fact affect the reflectance through some mechanism. At the same time, they found that that pressure was not a significant factor. That's in the right-hand side. However, if you go to an open system, in fact, there is a significant difference in the way the vitrinite changes. So again, it's a very nice paper. I recommend you back to read it if you have not. More recently, there have been a fair number of people who studied the pressure. The Delatoria and Bayon papers found, they studied a fairly wide range of conditions. They found either retardation or acceleration of reflectance depending on the pressure and reflectance ranges. So they're proposing some complex things going on. There are quantitative differences between their power law model and EZR0, but qualitatively they both have this feature of, let me see, I found out how to do this. The idea here is that you have a very rapid increase in the early stages and then it levels off. So this is the parallel reaction model, and this is a parallel reaction model. So qualitatively, in fact, if we go back to Huang's model, again, has the same feature. So to confirm that there's really multiple ways to approach that kind of phenomenon. You can take Huang's data and then you can fit to a discrete parallel reaction model, and I've done that, and that's shown on the left-hand side. Data at half of a kilobar at temperatures ranging from 300 to 450 degrees. And then if I take that parallel reaction model and compare it to the Bayon data, that I find something that agrees a little bit better than EZR0, but it's similar. So I want to emphasize that qualitatively people are seeing pretty much the same thing. There are quantitative differences, but qualitatively it's all pretty clear. The problem now comes when you go look at more extensively of all the work in the literature on vitrinite reflectance, and this was shown, I think, initially in a paper by Mike Lewin. So here are the coals. These are fixed time at a given temperature. So the coals tend to be up here, and the type 2 source rocks tend to be down here. So stating the obvious, there's just no way that the same chemical reaction model is going to fit this data and this data at the same time. EZR0 was, we noted at the time, kind of was between the two. If I take the parallel reaction model that I derived from Huang's data, it actually agrees much better with the coal data. So that shouldn't be too surprising since Huang's data was, in fact, based on a coal. And here's the same thing at 24 hours. You see the same thing, that E00 is between the coal and the type 2 kerogens. Well, I guess they're not all type 2, but sapropellic kerogens. And Huang's data, the model from calibrated from Huang's data, agrees better with the coal data. So let me go back to Vitrimat. The global chemical reaction models are convenient, but I think it's helpful to go back and look at what really is going on in more detail in the chemistry. So I'm showing again here the elemental balance equations, and also then the calculation of the elimination of water and CO2 at both laboratory and geological heating rate. Because these have lower activation energies, actually a separation of the two in terms of how they relate to each other. In other words, what I'm trying to say is that the geologic elimination material, it comes over a wider range than does the laboratory. So now I've compared in this some of the original data that was used to calibrate Vitrimat by Marc Montho on the Mahakan Delta, and then there's some later data by Francois Bahar on the Morwell coal. And if you plot the molar ratio versus temperature, what you find is that they're different. So again, stating the obvious, you can't have the same chemical reaction model, at least the parameters of the model, be the same when the data is different. So you can see an earlier elimination of hydrogen and oxygen from the Morwell coal experiments. And if you cross-plot these things on a Van Crevelen diagram, the Morwell coal comes down here, and Marc Montho's goes here. This was Vitrimat. This was calibrated to mimic what was observed in geologic data, a bit sharper curve than is seen here. And so that brings up one of the issues, that there do seem to be somewhat slightly different trajectories on the Van Crevelen diagram. Now, if you take this to the extreme of open pyrolysis, it gets even more extreme. But this could be a second order effect having to do with the nature of the chemical reactions involved. So it's fairly straightforward to change the parameters of the Vitrimat model to match this data instead of the geologic trend, and this dashed line is that model. It's a modified model, and this is not published. I don't really intend to publish it. It's included in a textbook I've just completed on the chemical reactions of fossil fuels. So it will be available shortly. But again, the point here is that if you have a spread of data, at best you have to decide which data is most relevant, or kind of take something in the middle of the range. The other aspect that could be modified in Vitrimat is the relationship between reflectance and the elemental composition. Here was the original plot from the Geochem Cosmochem active paper. The solid line is what we had done. There was an earlier correlation by McCartney and Ergen. This is down when oxygen is being eliminated. So the question is, well, oxygen is sort of a diluent. It's not very polarizable by comparison to hydrocarbons. So what should be the effect of oxygen on the Vitrimat reflectance? If we now go back and look at the calculated reflectance as a function of hydrogen to carbon ratio for all these laboratory experiments, you can see that the calculation is qualitatively correct, but quantitatively it seems to have a bit sharper slope than the data. But the data are really fairly consistent. But on the other hand, if you look at the deviation here, you're talking about plus or minus 0.05. So you can't really expect a chemical reaction model to really do any better than about 0.05 in reflectance. There was a paper by Matthews et al. In 2014 that looked at various correlations between reflectance and weight % carbon. They mentioned that the correlation of Vitrimat seemed to be about the best. It's very similar to one by Nebel from Exxon. When we developed this, we were told by people from our oil industry supporters that the hydrogen to carbon ratio seemed to work better with the data they were familiar with geologically. So that's what we pursued in more detail. But in fact, there were two different correlations: one with weight % carbon and one with hydrogen to carbon ratio. And EZR0 is calibrated on the hydrogen to carbon ratio correlation. Going way back in time, people have considered that there has been some sort of a break, we call it a dog leg, or you can use any other descriptor in reflectance. This is reflectance versus depth. Ulrich Ritter from the IKU published a model in 1996 that tried to increase the break in this curve. He basically took EZR0 and adjusted the parameters. And so that was actually quite some time ago that work had been done. To my knowledge, that was not picked up by very many people. However, more recently, Nielsen et al. Proposed a Basin %R0 as an improved calibration, and it really has a character very, very similar to what Ulrich Ritter had done 20 years ago. So here's now a comparison of these various things, reflectance versus temperature at heating rate of 2.8 degrees per minute. So here's the Basin R0 with this sharp break. These other, the Vitrimat and the modified Vitrimat come here. They don't address this sharper break. In fact, if anything, they make it worse. And the EZR0, as you can see, agrees with the hydrogen to carbon ratio as designed. So the question is, which is right? And this is part of the study that was involved Oliver Schenk and Ken Peters. Ken has been quite interested in the Alaska North Slope, and so here's now some work on calibrating a paleothermal history in that area. And sure enough, Basin R0 does work better than EZR0 for this particular case.
Holy crap.
So this shows the difference in maturities calculated depending on how you calculate the reflectance. And so the other way of looking at it is essentially when oil is generated. This is reflectance versus time, and there's a bit of a timing. So even though it looks quite different here, I guess I'll leave it up to you to decide whether or not you think this is a big or a small difference. But in any event, it's Nielsen provided a fair number of examples to support the idea that that this break is big. Now, other people I've talked to say that they don't agree, that they found that in fact EZR0 works better. So I'm not going to express an opinion on that right now. I think there's good evidence that EZR0 maybe does need some modification, but exactly what it is seems to be a bit controversial at the moment. So, in Nielsen's paper, he mentions that it doesn't work as well at laboratory conditions, and so here's just an example of this. This is nothing other than a further example of what he said in his paper. This is Basin R0, the green line, and it actually works quite well for the sapropyrotic materials. It's terrible for coals. here's now the model of Huang by comparison, and EZR0. So you can see that there's one comes into a bit of a challenge here. Do you want how much credence do you want to put on laboratory data for calibrating a model? Now, if you go back to the philosophy of BP back in the 1980s, they believed that you really couldn't calibrate kinetics on either geologic or laboratory data alone, and so they did a simultaneous optimization. And that's perhaps one approach that should be taken. But want to make sure that everybody understands that Basin Ro, even if it is better at geologic conditions, is not very good at laboratory conditions. So what is one possible issue? This gets back to this issue with the BP calibration, and actually a paper by Doug Waples, he was saying that, well, you know, people do a poor job of measuring kinetics, and so you're better off assuming a frequency factor of 10 to the 14th or 2 times 10 to the 14th. And there was Ken Peters and Cliff Walters wrote a paper which I hope should be considered as a clarification of the situation and not a complete disagreement with what Doug said. The reality is, if you're not very good at measuring kinetics, you are better off assuming a frequency factor of 10 to the 14th than 10 to the 13th or whatever. But it is possible to do better. The implications here is that we just assumed a frequency factor of 10 to the 13th reciprocal seconds. And so that means that if you have simultaneous agreement at geologic conditions, it will not agree at laboratory conditions, or simultaneously, if you match it in laboratory conditions, it will spread apart at laboratory conditions. So 10 to the 14th, which is more typical of the frequency factor that you do see for kerogens, tends to give you the same relationship between kerogen transformation and reflectance. So that's a fundamental question that people need to think about: is, do you believe that the kerogen transformation in the laboratory, in these various simulations, hydrous pyrolysis, confined pyrolysis, whatever, is the same, the reflectance is a function of transformation is the same in those laboratory experiments as is in nature? Here suggests that there is maybe about a 0.1% difference in that relationship if you use a frequency factor of 10 to the 13th. So I'm personally now more favoring a factor around 10 to the 14th, or maybe even a little higher. So I also want to point out that there's this 1, 2, 3 rule that can actually estimate the amount of this spread. This was a presentation I gave in an APG meeting, actually in Calgary in 1992 or 1 or something, way back when. The 1, 2, 3 rule is that if you have a relatively narrow range of heating rates, a change of 1 kilocalorie per mole corresponds to roughly a change of a factor of 2 in the frequency factor to give you the same reactivity at that temperature. And it will give you about a 3-degree spread in extrapolation. It was presented in terms of laboratory experiments giving a 3-degree error per kilocalorie per mole. But it works the same way, that if you calibrate on geologic, then you'll be off in the laboratory conditions. So I have dozens of trial models. It's not difficult. You can calculate. You can calibrate a model at geologic conditions, as agrees with Basin Ro, with a frequency factor that ranges from 10 to the 12th to 10 to the 15th, and there's no practical difference. These were just simple manual fits. You know, it takes about 30 seconds to adjust the parameters to get a fit here. So the point here is that there's really no way that geologic data alone can tell you what the frequency factor is within a factor of 100. It is really the comparison between laboratory and geologic data that can really constrain this frequency factor. So here's, let me see. Now the comparison to this other collection of data of hydrous and confined pyrolysis from the literature of these two, the frequency factor of 10 to the 15th seems to work better than 10 to the 12th. So what I'm proposing is that a frequency factor of 2 times 10 to the 14th is going to maintain the relationship between Vitrinite reflectance and transformation ratios at both laboratory and geologic time frame. Both the work by Doug Waples and myself, when you look at all the determinations of literature, the good ones, what you find is that the median value of the frequency factor is around 2 times 10 to the 14th. So that would seem to be a plausible way to fix the frequency factor in an optimization of kinetic model. So, but going back, I want to reemphasize that the best model for fitting laboratory data is really one calibrated on Huang's data, and this is again a parallel reaction model. So let's go see. You know, I thought I had a figure, but I guess it's maybe not quite yet. It doesn't. It predicts too much of a leveling off at geologic conditions. But so here again, repeating this conundrum, all laboratory data for humic coals suggest a rapid increase in the percent R0 in the oil window, and this increase is fundamentally incompatible with this pronounced dogleg during the geologic burial. So either there's a fundamental difference of what's going on, or there's a problem with how the geologic data is being interpreted. However, the agreement between Basin R0 and the dogleg seems to suggest that it's really more related to the vitrinite and sapropelic materials. I don't know that that's true, but it's something that I think needs to be explored in more detail. So one can derive a model that does a better honoring of Teichmüller's data. This is this 2 times 10 to the 14th model that has a bit more of a dog leg. This is Basin R0, and it doesn't increase as much at high temperature. I think this is sort of in the running for credibility, if you will, which leads us really to the conclusion: the best model is yet to come. I think there's Basin R0 is a very interesting hypothesis about the way that the model should be changed, but it comes at the cost of poorer agreement with laboratory experiments, and so we have to ask the question: what is that actually telling us? If we use a frequency factor more similar to that for decomposition of oil-prone kerogens, we can get better simultaneous agreement with geological and laboratory data. Laboratory experiments indicate that there are significant differences among vitrinites in different samples, and that suggests that there should be really a different model for vitrinite in coals and for vitrinite in oil-prone organic matter. The other way of stating that is that the suppression is quite likely related to the nature of the rock and not the pressure or oil generation per se. And each type of material, both the sapropelic and humic materials, have scatter of at least around 0.1% R0 from different workers. So, summary, what I've covered here is a bit of history that talks about the way that models have been explored to address computational time, effects of pressure, and vitrinite suppression. It's easy to enhance the computational speed using second-order reactions, fewer of them. There's a lot more calibration data now than there was in the late 1980s when we developed PSA so it certainly is reasonable to expect that we ought to be able to do a better job. Vitrinite reflectance versus depth has a sharper dogleg than calculated by Vitrimat and EZR0 in many geologic settings. Vitrinite suppression is more likely to be due to differences in depositional conditions and master interactions than pressure per se. So those are my my conclusions to date. As I say, I'd like to go back to the previous slide. The best model is yet to come. That completes my presentation.
All right, thanks, thanks, Alan. So this was a lot of stuff to digest. I mean, anyway, well, it was very very informative for me to get a better picture of the range of uncertainties that we are dealing with. And so I'm still trying to wrap my mind around what it means when we talk about Vitrinite suppression. So I guess people may understand two different things by this term. One is suppression relative to a model that they are using, or suppression relative to some sort of a trend that they observe in measured data. Can you comment on that?
Well, yeah, probably people are using it in different ways. I saw Noelle Sholkoff had joined, and it was interesting. In her course at Stanford, she was talking about definitional issues having to do with petroleum systems, and I had the same issue having to do with a discussion with Andy Pepper about expulsion. People use these words in different ways, and I really someone was trying to say something, but anyway, there was a paper in a presentation by Paul Hankley in Calgary that essentially showed that Vitrinite from different sources had different maturity, reflectance versus time and temperature. So
the issue of Vitrinite suppression may have to do, it may not be a Vitrinite suppression in a sense of something anomalous according to compared to what it should be. It's rather a reflection of the fact that we just don't know exactly what everything controls the Vitrinite evolution.
Well, I would agree with that statement. I mean, suppression just means it's different from what you expect.
Yeah.
The question is why are your expectations the way they are? And really, what I guess I'm suggesting is that if your expectations are that the Vitrinite should be the same in sapropelic and humic deposits, your expectation is probably wrong.
Yeah, and another issue I wanted to comment on, the difference between calibrating to laboratory data and calibrating to geological data. When we calibrate to geological data, we are really including the influence of our interpretation of geological history and our model. So we cannot really subtract the issue of uncertainty of our understanding how the rocks actually evolved and how the basin evolved. So yeah, I think it's almost an unsolvable issue that there will always be differences between the two approaches, and we don't exactly know what the reasons are. Is it because our basin model is wrong and not reproducing the pressure and temperature burial history correctly, and then leading to different calculated Vitrinite, or is it something about the actual measured geological data that makes it different from from laboratory measured data? Probably both.
Yes. I think it's really tough to calibrate any model strictly on geologic data. You're sort of chasing your tail.
Yes.
And I think there's a lot of merit to what the BP people did, of saying that you really need to use both laboratory and geologic conditions to calibrate your models. The laboratory data can tell us certain things. It tells us definitively that there are differences between sapropelic and humic materials. Mm-hmm. And if you don't take that into account in calculating and calibrating a model from geologic conditions, then you really have to have a good reason why the geologic conditions should be completely different from the laboratory conditions.
Okay, anybody else has any questions? You can either speak up or you can try to type it in the chat window.
Yeah, this is Steve Cruz. Can you hear me?
Yes.
Yeah, Alan, we've already gone around and around this, but I wanted to ask another question to clarify this difference between the material that's in the deposit. And, you know, it intuitively seems really reasonable that you would get different behaviors for sapropelic and humic material and so forth. But are we, there's that voice again. Are you saying, though, that the vitrinite itself, the actual particles of vitrinite, have a different origin in these different deposits, or are you saying that the influence of what's around them affects the reflectance?
Well, it could be both. I'm not a petrographer. I will defer to other people who understand that a lot better than I do. I remember talking to a person from it was Phillips Petroleum in Bartlesville many years ago, and he had done some experiments where he took the same vitrinite and put them in the presence of different materials during laboratory pyrolysis, and he did see differences in the resulting reflectance. So that there is some laboratory evidence that says that you can take the same vitrinite, put it in a different reaction environment, and you will get a slightly different reflectance. That, to my knowledge, that work was never published, and maybe there's other papers along that. So I think that is one thing that can happen. The other thing that Andy Pepper suggested to me was that if you have a deltaic deposit where you have the material is essentially longer in the water column, before it even gets in the sediments, it could have changed in ways that are different from if it's deposited in a swamp. So there's a whole range of things that could be true. I'm not really an expert in that to be able to know what is true.
Okay, that's an interesting idea. And then overlaid on top of that, of course, is the ubiquitous problem of whether people are really correctly identifying vitrinite. There's a lot of dark things in the rock.
Yes.
Okay, anybody else?
Okay, so Noelle has had something that popped up here. Says maybe her camera is not working, or her microphone. Says, I think geologic evidence is clear that vitrinite and humic versus sapropelic rocks behaves differently. You can see the effect when samples are taken all up and down the well rather than just over one small interval. And she adds, she's unable to be heard on the mic. So that's her comment. So now she's written another chat, a plea for more vitrinite analyses on more samples.
Alan, again, thank you very much for doing this for us. It was very nice review for me, which I needed for a long time already. And so I hope to have the video ready pretty soon to put it online and put it in the archives. If anybody else has anything to say, please say it now. Otherwise, I will thank you, everyone, for attending again. And thanks again, Alan.
Well, you're very welcome. Hopefully it didn't disappoint people in the sense that we always wish that things are simpler than they are, but unfortunately there are still some questions here.
Oh, this is good reality check. We need to look back at these issues over and over again to remind ourselves the amount of uncertainty we are dealing with. All right, so I guess we can close the session now, and I'll talk to you next time when we arrange some other interesting presentation.
Okay. Yeah. Thanks for all the attendees.
Thanks, Alan.
Bye.
It was common whenever you did a Vitrinite reflectance measurement to also extract the organic matter and just have a look at what the GC profile looked like. And, that's a pretty good indicator of the maturity state of your sample, actually, but hardly anybody does it anymore.
Yeah, certainly. When you go back and look at the textbooks, people look at all sorts of issues, and I don't know. I'm not a practicing Basin modeler, so I don't know how much of that is still used. I guess I'm work a lot with the biomarker people. Stanford has Ken Peters and Michael Dallin, influenced by the Chevron work.
Yeah, biomarkers has had a lot of influence on the discipline for many years and solved a lot of problems and provide a lot of elimination. But biomarkers are part per million quantities in oils and sediments, and I think we've tended to neglect some of the bulk constituents in favour of going to the much more interesting biomarkers sometimes.
Yeah, and I think the biomarkers are better in the lower range. All of the adamantine type materials are better at high maturity. Yeah,
there's new calibrations now that have come out for fluid maturities through the shale work that's been done. Geomark guys probably seen calculate a thing called VREQ now, which is based on aromatic isomerization right from the alkyl benzenes up into the polyaromatics. And they tend to do a better job, I think, of giving relative fluid maturity, but fluid maturity itself is a very nebulous concept if you think about what it means and what its relation is to sediment maturity. So that's probably a topic for another seminar.
Well, yeah. So it reminds me when back in the 1980s there was this was a stearine isomerization, and then there were many arguments and studies trying to figure out how much of this was an actual chemical reaction versus competitive generation and destruction reactions, and because the activation energy that came out seemed to be really nonsensical as far as a direct chemical reaction. And I don't know.
What Andy Pepper is referring to with the transformation that take place when you allow land plant organic matter to be deposited in marine sediments after a period of flotation or sinking or whatever is related to that, I think, because you're getting a diagenetic effect when you can get what appears to be the same as thermal maturation happening in ever wet sediments just through diagenetic reactions. So when you get that happen, sulfur gets in the way of that, so if you have any contact with land plant matter with seawater, it will alter the starting point for the thermal effects.
Yes.
Okay, I think we've exhausted the audience and the conversation, so I will just close down the session now, and yeah, talk to you some other day. Thanks a lot again.
Okay. Yeah, thanks for organizing, David.
Yeah, thanks.
Thanks, Alan. Thanks, David.
Yeah, thank you, Andy, for attending also.